is predicting human motion for human-robot interaction and collaboration. And I am Professor Alberto Sanfeliu from the Institute de Robótica e Informática Industrial. And let me see. Sorry. Okay, and then what I can explain is first, a general architecture is quite generic, but you will understand why. And then I will use that for explaining specific cases of human-robot task interaction and collaboration, and also how the motion prediction influence the human-robot task interaction and collaboration. Okay, now I'm going to show the first is this generic scheme that is quite it is new in one option, in one part, that is the part of the intention. You can see here two agents. Actually, I'm going to explain everything with only two agents. It's going to be one is going to be a robot and another is a human, and both the information from both is perceived by the first agent, for example, the robot. And in this, but it's not only perceived, but also the intention of the person's gonna be perceived, and also the person can give a specific intention. And both of these information, the perception and intention, that is the main issue is basically always has been the cycle has been perception action, but in here when we have human-robot task interaction and collaboration, is a new ingredient that is perception, intention, action. These three are the basic elements. And actually the intention, then some of the intention is perceived by the perception system, by others cannot be perceived. And that is something that we call implicit. That is the one is observed or perceived, and explicit, the ones that has directly not information, and the person explicitly shows the intention by whatever element. And then all these two elements, perception and intention, goes to something that is called situational awareness. You probably know this concept because it's quite old one, but is our, I think it is quite appropriate now when we introduce the part of the motion. Okay, and then one part of the situational awareness is what is called current situational understanding. From the perceived part and the intention perceived and explicitly given, we can understand what is our present situation for a specific task. I will explain later on in the specific details in some applications. And then the future situation projection, knowing what is our situation at present, what is going to be project in the future, what is going to happen. And also this projection is the part where we need the motion prediction and from the skeleton or from other elements that are moving, or also you will see when we are doing a company, where is the person that is accompanied, what is going to be, and we have to project what is going to be that, what is going to be in the new time steps, what is going to happen. And from this information, then we can start to make our own decisions. And actually, the first thing that we need to do that, it is to select which are the roles of the different agents. And these roles are, for example, master or slave, or collaborative, or neutral. Neutral means that we are predicting something that is strange, that we don't expect, but still there is intention of the person to do the task. Or could be another one that is called adversary, that is actually the person that is doing theoretically a collaborative task together with the robot is not doing that and do not want to do that. And then knowing that, and in principle, the idea it is a collaborative action, then we can do the collaborative plans. And each one of the agents will create their own collaborative plans. And once we have these collaborative plans, then we will be able to do the collaborative actions. And this cycle is repeated every time. And as you can see, always we will perceive, we will be always in tension, we will go to the situational awareness, we will do our predictions here in this part. And actually, I'm sorry, I don't know, you can see my, okay, I'm sorry. You can see this part of the current situation and the future situation projection. That is where it's going, all the part of the motion. And then they may take the decision. And this is the cycle that is gonna be doing every time. I'm gonna go to different examples of that in order to show what is the difference in between when there is a collaboration and the prediction of motion. Okay, I'm gonna talk a different kind of experiments that we are working on. One is accompaniment, another is approaching, another is searching together to one robot and one person that try to look for an object in a very large area. Another is the operation of Hanover between robot. This, another is object transportation. This I will not explain now. We are present in another conference, this kind of work. And there is an additional one, there is a harvesting and pruning. There is inside of what a European project that is called Canopies. Okay, let's start by the first one. There is motion prediction in human robot accompanying and approaching. Okay, we have two different tasks, but let's going to start with accompaniment. The accompaniment, it is a robot that is accompanying one or two persons or several persons. Let's going to think about that this accompany one or two persons. They got to reach to a goal. And at this moment, the robot has to predict the motion of the bystander. Whichever bystander is here or another object that is moving, it has to be predicted. But also at the same time, has to predict the person that is accompanied, or the two persons is accompanying the robot, in order to modify the path planning and the execution of it. Okay, and that is something that is done online every time, that is moving around and is trying to reach a goal. And in this case, as I said before, the person that is side by side is trying to do a collaborative action that is being accompanied, or could be that is neutral. Then for example, it falls down, then it still wants to continue, but because it's fall down, then the robot has to stop, and then and the prediction in the principle of what is the motion of this person is gonna be stopped because this person is fall down. And then, or could be that the person don't want to continue moving together with the robot and goes away. And that also has to be predicted by the system. Okay, in the other case, the approaching is very similar to that, and the only thing it is, in this case, the robot has to approach a specific position, but this people is moving, then actually has to change every time the motion, and also it has to predict every time where are going to be the persons, where are the rest of the people is moving around. Okay, in this case, you can see that in the intention is going to be implicit. We have, for example, leader information, where are the person that be accompanied, or where are the bystander, or where there are the other objects. Could be leader, could be the camera, whatever sensor is used for detecting that, the intention. And then the system has to do these predictions of the person to be accompanied, of the bystander, and the robot modified online its motion navigation plans and actions based on future agents' motion path. That's clear, no? That is not a big problem. However, this is going to be done every time, and the robot has to adapt every time to what is going around. And you can see here an example of what we did with our robot, one of our robot, TV robot. Then the robot was moving around in an area when people is moving, do not at all that where the robot it is and where the robot wants to go, but the robot knows where to go. And it has to change its prediction every time, and it has to modify its plans online, taking into account what is the situation at that moment, and what is the future, what is going to happen in the future. That is, what I say is going to happen in the future is what I say that is inside of this situational awareness. There is a key issue for understanding what is the best option for the robot in order to really collaborate in this case is a navigation, but you can see here the accompaniment or the approaching, okay? Every time it has to adapt and to modify and to understand this situation, although people is going around, is moving and can do many things different of what is expected to be done, okay? And then the key issue is to really predict every time what is going to happen. Okay, now let's go into motion prediction in human-robot Hanover task. Then in this case, in a typical Hanover task, there is 4 phases. One is approaching, another is pre-contact, another is contact, and another is release. But again, in here, the robot has to always do the motion prediction of the person, not only the body itself, but also the end effector where the object it is in order to be delivered, okay? And again, the roles of these persons can be master-slave, can be collaborative, can be neutral. For example, the person, instead of giving the object, is at this moment, I don't know, there was a call and they tried to put the hand in another part and that kind of things. Or could be that the person decides not to continue and be adversary, okay? In this case, in any of these cases, the robot has to detect that situation and predict what is going to happen next, because the robot has to decide if it continue moving, where to go, where the arm has to be in order to pick up the object, or if the robot has to stop, or for security issues, the robot has to do another motion or another. And then in this case, again, the intention is implicit, could be explicit if the person gives some signals, for example, gesture or whatever. The situation is again the 3D human body, and the robot again modifies online its motion and actions with respect with the future motion predictions. In this case, we use an attention deep learning method, algorithm, in order to predict the skeleton of the motion prediction, but also we have intentions. And we also can predict the intention of the motion prediction. We say we can see what is going to happen due to the situation. Is the person is going to change the intention at that moment, and then we use not only the intention, also we use the context. We use we use the motion itself. We use the end effector. We use the obstacles and objects that are around, and we use the intention. And all this information, we want to do the prediction of the motion prediction and also to the intention of the motion prediction, okay? And that is something that you can see here. Then that is in this case, a simple case. Then is a person is approaching with the object, the robot is moving and try to pick up the object. And then it has to, again, predict all the different situations that are in this case, okay? And that's we do with this kind of attention deep learning method structure. It's a transformer, okay? Now, also, we do similar for collaborative searching of an object. And in this case, I say before, there is a person and a robot that have to look for an object. And these two agents, the robot agent and the human agent, has to organize their plans for doing the search. The search is in a very large area where it is around 30 meters by 30 meters. And then the objects are very small. There is purchased pieces put in the floor, and that is not easy to see. But the only thing is the robot has not enough. So we put it, then the information when it arrives closer to the object, then we say that the robot has reached the goal. But the person has to look at that and using their own perceptive sensors, no? And then both has to collaborate doing this search. Now, you can see the robot use the information of the sensor in order to track what is the person. It has the environment. It has some, and it has a model simulator from the environment, and it plans its own path, but also it plans the motion of the human. And how we in this case, the motion prediction is the robot is detecting where is the person when it's visible. When it's not visible, cannot predict, and only can use the pre-plan in order to think where the person could be. And actually, in this case, the motion intention is implicit because using the sensors, or is explicit because the person gives his or her intention of the area to explore. And there is a future motion prediction of the person that shares the search. And the robot modified. In this case, I talk about offline. You will see why I talk offline. Okay, let's see an example of what is going on. The person and the robot shares a map and the information of the plans through mobile. Sorry. Just a moment. Okay. Shares using a smartphone, and this smartphone has the map, and with them they can share information of the intention of the person, where they're gonna go to search, and the robot in this case creates the trajectories where the robot is gonna go and where the person is expected to go. And then the robot, every time, it is predicting what is going to be the person, and then it changes. Well, it goes with its trajectory, but it can change the trajectory depending on what is going to do the person, in order that they do not overlap where the area that they both are going to search for. Okay. Now, in this case, you can see here the robot computes what the person do. The robot is gonna also predict, and it shows to the person in order that both agrees or disagree with the plans, with both plans from the robot and the person. The person always can modify the plan if he do not like what is gonna be. No, and then again, in here the prediction it's explicitly given by the person that says what wants to go, but also it is sometimes it is looked at by the robot, because it is computing where is going the person and also what is going to be in the future the person. Okay, in this case both are separate and there is not big issues, but the issue is not overlapping areas and trying to look to overcome all the most area in order to look for that the objects themselves. Okay, and you can see that in a faster view, and then they can change with this and then finally the robot can reach or not the goal that is what they're looking for. Okay, now there is another one that is still we are working on that. We are now working but not finishing this part. There is motion prediction in human robot harvesting and pruning. In this case, the point it is we want the robot collaborates with humans for harvesting and for pruning. And you can see this done only by humans. Okay, on the right, you see the person and how he's doing the process of cutting. There is a vinegar table vinegar that in principle cannot be touched, although this person is doing that here, but it has to be cutted without touching the grapes. And on the bottom, it is the process of pruning the tree. That is quite complex because it has to be detected where where it has to be cutted, and then when it's cutted, also the branch can fall down or cannot be fallen down. You can see here they do not fall down. And then what we do with the robot. Okay, and in these cases, also what we want it is to the same scheme. We have the motion intention. The part of implicit is observed using LiDAR and other sensors, for example, camera, and explicit, then the person indicates what is going to do. For example, by gestures or using some kind of wearable elements, or by only talking. And then the robot has to predict what is going to be the human body of the farmer and the bystander, people in this around, and how they can collaborate. And the robot, in this case, again, modifies online its motion plan and action to do the task. You can see here the detection of the grapes, that is directly from the field, and what we have done up to now. And there is examples with real data. And at the bottom, you see in this case, the detection of the person. And in this case, this person is doing the harvesting and doing the part of the process. And then we are detecting the skeleton of the person and also predicting what is the motion of this person. You have to realize that the robot in this case is going to be close to the person, and they both are going to collaborate in part of deciding what is the next action. For example, the robot can take out the leaf in order that the person can take out the leaf in order that the robot can approach and see better the grapes and the peduncle, because actually the robot has to cut the peduncle on the top part, and many times are quite complicated to see what it is and what is the position. That is in the case of harvesting, but in the case of pruning, there are many times that it's very complex to see what is exactly the point where it has to be cut. And in some cases, it has to be helped by the human. That's clearly then the idea. It is that the robot finally works autonomous, but that is not going to be true for all the cases. And that is the reason why we want to have this kind of human-robot collaboration for these complex cases where the robot cannot do by itself the task and has to collaborate with humans in order to help the human help the robot, or the robot or the robot helps the human. In both cases, we need this kind of to know what is the intention of the person, what is the next position in the future, and how the robot has to actuate. For example, one issue that is interesting is when the person is indicating where is the point to be cut or taking out the leaves, the robot itself has to change the position in order to see from another point of view, in order to realize that it sees something that the person is showing or is trying to describe. No? And that is this kind of situation is where we need to know what is going to happen in the future in order that the robot actuate and properly actuate. No? And you can see here the gestures. That is another of the information that we need. It is pointed out what is the position where the robot has to go or has to do. No? That is the kind of operation that we are going to do. And this year we're going to work on this part in the real fields. Okay, that is what I wanted to explain about motion precision in human-robot interaction and collaboration. If you have any question, please let me know. Okay, I don't know if...
Thank you so much. So are there any questions? So people from the assembly, you can just stand up and go to one of the mic in the room. And perhaps people which are online, you can raise your virtual hand and then you can also speak up from there. Maybe I start with a question. Really interesting topics. My question is simply, how do you account for safety in those different contexts? Like you talked about navigation, but then also here about the last harvesting part in pruning. Do you reason about some safety concepts in these environments? And do prediction play a role in it?
Mm-hmm. Yeah, actually, in all these contexts, there is some safety issues. And one of the first ones, we use the prediction. One of the part of using the prediction is actually a safety issue. We don't want that the robot, in principle, is too close to the person. However, for this operation that actually that has to collaborate in very close mode, what we use the prediction is for lowering down the motion of the robot in order that the person perceive what is the robot is going to do, and in some way also trust on what the robot is going to do, and can do the operation without risky. But in all of them, we have that, probably except in the one of the searching that is than the person, the robot, or far aware. In the rest, all there is a very close, and finally there is in the Hanover, for example, finally there is a contact, a physical contact with in the object. No, in the case in the part of the accompaniment, there is no contact, but we also try to maintain some distance, and the robot predicts what is going to be the person and then tries to avoid that the new situations. Okay, there is, we also use part of we also try to anticipate what is going to do the person using these predictions. Okay, and then we have algorithms to anticipate this action, taking into account what is, for example, the bystander going to do, or what is the accompanying person, or what is going to be the arm located, and try to anticipate different actions, and always taking into account the safety issue. No? That is.
Thanks. We have two questions. Maybe.
I have a question actually. Sorry.
So there was.
Please go ahead.
In the room, we have two questions, and so maybe Alex starts from the room, then maybe followed by Dagmar, and then another question from the room. So, please.
I hope you can hear me. Thank you for the talk. You showed a lot of tasks like perception, intention, prediction, decision. What would be for you still the hardest research question to address out of all this for like our researchers? If you had to pick one, what is according to your experience the hardest one yet it has not been solved?
Excuse me, can you repeat, or someone can repeat, because I listen very low and I cannot.
Okay. So maybe because they're a bit far. So the question is, I'll try to repeat, what is, according to your opinion, given your amazing and long work on this topic, what is still the open research question that we will need to solve, right? You know, what would you recommend to new students to research? I hope this was clear.
Όχι από το VM των Windows, από το software που σου δίνει τα VM. Είναι virtual box. Ναι, έχει κάπου, νομίζω, setting για να κάνει shared folder. Από το post στο VM, στα settings.
Alberto, could you hear us?
Okay, I don't know if I understood very well the question. I'm sorry for that. But yeah, okay. What I say, what is the open issues in this task?
Just one. I mean, just one open. Like your hardest. If you had to pick one, what is for you the hardest task that's still
the hardest
not being solved?
Okay. For me, there are several that are hardest. I don't know which is the hardest one, but the one for, I say, for example, I showed that is we have to predict what is going to do the person, and to predict, for example, only in the trajectory, to predict if the person is going to collaborate or not collaborate. That is not really the hardest one, but is one that is going to be quite important, because if the robot perceives that it's going to change the part of the trajectory, then it has to anticipate and modify his behavior, but it has to be done in very fast mode. And then it has to predict what is going to happen in the next. And if something is complex, that is in a simple situation, that is not too complex. But in a complex problem, then there are different elements that are moving. This prediction is going to be very difficult, because you have to realize what are the different objects that are moving, and what is and the robot has to understand the intention of the person, then what kind of task is going to do. And this is, for me, is a quite complex issue, because if not, the person will not feel comfort with the task, and then could be that the person decides not to trust in the robot and forget about it. No, and then this is an issue that for me it is quite important to understand that. But also, when the robot decides to with the information that the prediction anticipate, then it has to do in a way that the person feel trust again with the robot. If not, again, we will find that there will not be a match in the collaborative task. Okay, and that are issues. And then going down, what that means, the good prediction of the 3D skeleton, it is for me now one important issue. No, it's quite a bit, and then we dedicate quite a lot of time to that one. No, but that is one of them. Okay.
Thanks, Alberto. So looking at the time, we have 2 questions quickly. One from Dagmar online, and then it will be followed by Alonso Mora in the room. Thanks.
So I think my question is somewhat of a follow-up or the similar topic as the first question. In your harvesting and pruning task, I was wondering how the division of labor actually then works, and what you just explained, as in predicting the collaboration of the human partner is what decides, or what the robot decides upon whether to do that same action or not. So to put in simpler terms, how is the division of labor decided or arising in the interaction? And maybe specifically when you do it, what type of actions how do they get distributed?
Okay, let me explain something else. Before you do this task, there has to be a kind of learning of the task itself, okay, between the robot and the human. And this process, this knowledge has to be in the robot itself, because it has to learn before this task in a collaboration. In order that the robot knows what is the normal plan in doing the collaborative task. Then that is what has been learned. However, the human can behave in very different ways, okay? That means that do not follow exactly what has been learned. And that implies that then the robot has to adapt to what is going to happen next. And this is what we need this kind of prediction. We need to know if everything goes right, then the prediction is very easy. You have something to follow, where is the arm going to be, where is the person is going to be, and that's all. And then step by step, and that's finished. However, the person do not exactly do that. Many times change immediately the way of moving the arm, or the moving the head, or the moving the, and then in this case, the robot has to adapt every time to that. However, with learning before what is the plan, then it has additional information to know what it has to do. If it has to change the position, we have to stop or slow down. And that is something that we will use the previous information, and we will match with the prediction in order to know what is our situational awareness, actually. What is the situational awareness, and what are the potentials, different plans that the robot can do. That is what
I understand, the adaptation part that you just elaborated, but my question was further directed how the robot learns in the first place, what he knows, what the robot knows in the first place. What does it mean to have as the basis before adapting to a new human? Because does the robot need to do the task by itself in the first place and then to collaborate?
Yeah, the robot first, it will do the task alone, completely alone. Okay, that is clear. The second part that has to be learned is how, when there is a human, how they collaborate to do this task. And this has to be learned using the robot and the human. What we are doing now is using virtual reality, augmented virtual reality, doing this learning process. So with virtual reality, we use both the human and the robot in different modes. And we create a data set. And with this data set, we create the models of what is going to be the behavior of the robot. And with that, we have the context, what is going to be the different application or the different plans. And that is going to be used when the robot actuates. And then the robot is going to predict the motion and match with the information that it has been learned, and then try to match that.
Sorry to interrupt you. Thank you again. Maybe very last question from the room, and if we can be, looking at the time a bit quicker on this one, just for giving then the words to the next speaker.
So thanks, Alberto. So in one of the videos of the prediction of the humans, it looked like you are also doing some level of uncertainty propagation of those predictions. Could you elaborate on how do you get that uncertainty prediction for the predictions, so the uncertainty propagation in the predictions? Thanks.
Okay, if I understood well, I see you're asking about what is the uncertainty, in the predictions. We actually what we have, it is not we have an uncertainty area. The prediction, it is not complete. It is not deterministic. It is stochastic. That's clear. And then we have in our motion, we use not only the base itself, but also the arm when it's moving around, and it has an uncertainty where it can be. Okay, and this uncertainty, it is used to know. It is used when we are in the last part. For example, in a Hanover operation, then it has to reach the object. We have the uncertainty of the prediction of what is going to be, and then the robot has to be in a position that is clearly easy for it to move in any of the potentials position that is going to be the arm. And in the last, we use visual surveying actually in order to approach very closely. In this case, we can really reduce the uncertainty of the prediction. Okay.
Okay. Thank you.
Okay, we thank again Alberto for this interesting talk and also the nice answers you gave. Thank you again.
Okay, thank you.